It's a group quiz, so I have the group quiz. Do you want the group?
No, it's an individual.
Oh, it was an individual quiz? Oh, okay, I'll do the same one.
I'll figure it out. All right, so the second third of chapter 16 is looking at acids and base titrations. So based on what we know now about strong acids, strong bases, weak bases, and buffers, we can now talk about how we use those guys experimentally to determine quantities in solution. So, okay, titration is a method to determine the quantity of an acid or a base in a solution. There are really two big things to know. The first one's going to be a definition, so using the lingo of titrations. We have this thing called the equivalence point. And the equivalence point is where one reactant has been completely consumed by the other. So the equivalence point is where we had two reactants and one has been used up. So then the other thing to know in terms of conceptually about titration let's say we're reacting a strong acid with a strong base, right, a strong acid and a strong base. What are the two products that get made when I react a strong acid and a strong base? Salt and water. So what would we expect the pH to be? Neutral, right? Still true. Makes a salt water, which means its pH will be 7. So that's a good guidepost that if you have a strong acid and a strong base reacting together, at their equivalence point, the pH has to be 7. Because you're saying all the strong acids react with all the strong base. So then let's look at the other two cases. Right, strong makes a salt and water and definitely gets a pH of 7. If I have a strong acid with a weak base, we should expect it to be acidic, right? Because a strong acid is going to convert all that weak base to water and then still have some acid left over. So we expect that pH to be greater than or less than 7 if it's acidic, right? So at the equivalence point, if we have a strong acid and weak base, we expect the pH to be less than 7. So in the third and final case, let's say I have a strong base reacting with a weak acid. Would I expect the pH to be less than 7, equal to 7, or greater than 7? Okay. All right, so if we know those points for different types of reactions, let's go ahead and take a look at each one of these cases. We're going to do a strong titration. Then we're I think I have a strong acid, weak base, and a strong base, weak acid titration. And we'll see what happens as we add the two reactants together. So now's a good time to fish out your calculator. If you don't have it handy, you will need it. We're going to do a lot of calculating today. All right, so let's think through an experiment where I want to know what happens to the pH as I add 0.1 molar HCl to 50 milliliters of 0.1 molar mystery. I apparently forgot to finish my sentence. Sodium hydroxide. All right, so the first thing I want us to look at that's not being spelled right. E-Q-U-I. First thing I want us to do is determine the equivalence point. Where the equivalence point is where moles of reactant for each of the reactants are equal. So there is no limiting reagent, right? They're equally limiting. They're the exact same number of moles. So the equivalence point is where both reactants have equal number of moles. So which component do I figure out first? Which one do I have the most information about? Sodium hydroxide or the... Which one can I figure out moles from first? Right, sodium hydroxide. So if I do this, I have, right, 0.01. All right, so I know I have that many moles of sodium hydroxide. I want the moles of sodium hydroxide to be equal to the moles of HCl needed. So before you jump ahead and say, oh, well, I know that, you have to write your balanced chemical equation. In this case, I happen to have it set up that's 1-to-1. That may not always be the case, right? I could try and fool you. So we'll write our balanced chemical equation. So it's just a good habit to get into. Right, so that's our hydroxide from a sodium hydroxide, and we always write our strong acid as a hydronium. So yes, in this case they are definitely 1-to-1. So the final question is, how many milliliters of the hydrochloric acid do I need to reach equivalence point? So write the moles of the equivalence point, they have to be equal to each other. And if I know the molarity, I have to figure out milliliters. I don't think I did my calculation right up here earlier, did I? No, that's definitely not right. All sure anyone else is participating today because someone caught me on that huge, huge error. All right, so how many milliliters do I need if I need 0.05 liters? Right, 50 milliliters? That makes sense? Could you have guessed that already? You could have, right? Because they're equal molarities. It's a 1-to-1 ratio, so you would expect it should be 50 milliliters of each. All right, so what we're going to do is, follow-up question. What pH is this point, the equivalence point for this reaction? 7, okay? Okay, so the pH equals 7 at this equivalence point. So now we have one piece of information about what happens to the pH as I add hydrochloric acid to my sodium hydroxide. So I want to look at 2 other points. So we just did this one, right? So it's the same question, just second page. So we just did, if we added 50 milliliters of hydrochloric acid, we know the pH would be 7. I want to know what the pHs would be on the way to 7. So I want to look at the initial pH and figure out what the pH would be. Now I'll look at one point that's halfway between the initial and the equivalence point. Before we get started, let's make some educated guesses, right? So we're imagining a reaction that looks like this. All right, so I'm adding HCl to my flask that has sodium hydroxide in it. So what would you expect the pH of the sodium hydroxide flask to be? 7, greater than 7, less than 7. We expect it to be greater than 7, right? Because it's a strong base. Is at this initial point, so we're at just NaOH, is there any acid in my solution? No. How would I go about figuring out a solution that's just a strong base? All right, so all I have is a concentration. I just have a concentration of strong base, so I can just use the POH. It's the only thing in there. There's no conjugate acid base, there's no buffer, there's nothing else in there, just strong base. So what is the pH of this solution? 13. Does that make sense with what you know about strong bases and pH numbers, right? So we expect it to be strong. It's right up there at the very brink of being the strongest number we could possibly be. All right, so now we're ready for halfway. All right, so I'm now halfway through my reaction, right? I'm starting to add the strong acid to the strong base. We have this reaction going on. Do I have a buffer? No, there is no buffer. How am I going to figure out what the equivalence point is going to be? The word equivalent should make you think ice chart. We're going to need an ice chart. Because E stands for the equivalence or equilibrium point, I guess, not to be confusing. Equilibrium point. All right, can we start on our equilibrium calculations yet? No, because we have 2 different volumes, right? Because I have 50 milliliters in here and I've added 25 of that. So I can't use the same volume, right? They wouldn't cancel out in any kind of equation. So how do I get rid of the volume issue? We're going to move to moles. So I have two different volumes in there. I can't just use the molarity. So I want to figure out moles of OH minus, which we figured out on the previous page. So we had that before. So now I want to figure out moles Would you expect these moles to be equal? No, right? Because we already did the equal point. Now we are ready to put it into our ice chart. So we have our initial number of moles. Which component is going to be used up first, the sodium hydroxide or hydrochloric acid? How do we know it's hydrochloric acid? Right, it's the limiting reagent. There's less of it. Right, it's going to get used up first. So how much hydrochloric acid would that leave me at the equilibrium point? All right, 0. And then I have this much base left. Can I plug that into a pH or a pOH equation? No, those require concentrations. How do I get from moles to molarity? Right, so my new volume Right, so at this point, the E point, the equilibrium point, you have 0.0025 moles of hydroxide and a total volume of 75 milliliters, right? Because you had 50 of one, 25 of the other. So my new volume is 75. So these titration questions aren't new, right? It's nothing that we haven't done in all the other ones. It's now just putting together all of it at once. And these are going to require a lot of practice on your part to be able to do them quickly. All right, so now we can plug it into pOH. Does that pH make sense in our trend? Yes, right? Because we expected it to be less basic, but not neutral. So we have a pH of 12.5. What does that tell you about the components? Which component do we have more of, the base or the acid? Right? We have a lot more base still, which is what we showed in this ice chart. There's still a lot of base in that reaction. So we would expect the pH to be still pretty close to where we started. All right, that is the easiest titration question. All the other ones are going to be much more complicated. So, over spring break, I know you have a million other things to do, but I would highly suggest starting to work on the Mastering Chemistry for next week. Because while there's not a lot of problems, that took us 20 minutes. And that only was a very simple problem. So, congratulations. Paul.
Are there any like specific book problems that we could work that, I guess like in previous chapters, they put book problems that kind of go, I guess, a different route than what we've been taking in here. So are there particular problems that?
I'd say go through all the worked problems in the chapter, and then at the end of the chapter, every odd problem has the answer at the back of the book. So those would be good ones to work through also for some extra practice, just to make sure you're setting it up correctly. All right, so then how about we talk about what if we didn't have a weak acid and a strong base? Oh, what if we didn't have a strong? Yeah.
Just real quick.
Yeah, ask away while I get ready.
I guess why is it that H3O plus? I understand that. I mean that's the same thing as acid. You replace that with HCl, and also why not do the IAs chart then because you're adding.
You certainly could have.
Okay.
Yep, that would have been fine too.
Okay. Cool.
Yeah, because titration, you could certainly do an IACE chart to keep track of what else going in there.
Okay.
Depends on how confident you feel.
Gotcha.
We're going to do IACE charts in these next sections just to kind of get us thinking through what's going on in titration.
Okay.
And then the H3O plus is just personal preference.
Okay.
By using our Bronsted-Lowry definition, it's more appropriate to write as H3O plus. But all right, so let's move on to the trickier cases where we don't necessarily know exactly what the pH is going to be at every step. So there are 3 key parts to a titration that we're going to look at every single time, just like we did in the strong. We're going to look at the pH before anything's happened. So in this case, the pH before I've added a base. We calculate it from the weak acid Ka and the acid concentration. All right, so before anything's added, and I just asked you regular, what is the pH of a 0.1 molar acetic acid solution? You've done that? You know how to do that? Using the Ka, figure out what the pH is. We'll look at the pH at the equivalence point, where the moles of weak acid are equal to the moles of strong base. That one's the tricky one because what do you see right there? It's a conjugate acid and a conjugate base in the same solution. It's a buffer. So at these weak, strong reactions, the equivalence point produces a buffer. Which means those will be two-parters. So then the final point we'll look at as the pH at the half equivalence point. The pH is equal to the pKa. If they are equal to each other, what does that tell you about the concentrations of the conjugate acid and base? Right? So we know some things about all 3 of these points that will help us figure out if we have made a good calculation or not. So as you're calculating along, you know things. They can be like, oh wait, if I'm getting a pH of 13 at the half equivalence point, I have gone astray somehow because I know that pH is supposed to equal pKa. So hopefully there'll be guideposts to your calculations. All right, we are just going to have time to start this problem. We'll do the first point or 2 of it. I'll make sure you have enough time to do your quiz, and then we'll finish it the Monday after spring break. Unless you want to finish it on your own. You're more than welcome to. Work through it on your own, solve some problems. Today we'll do A and C. And we'll save B for after break, 'cause that's the longest part of it. All right, so let's say I am titrating ammonia with 0.1 molar hydrochloric acid. So if I think about my sketch, right, there's my Erlenmeyer, here's my burette. Which component is in the Erlenmeyer? The ammonia or the hydrochloric acid? Right? Part of this is reading the problem to figure out which one's in the flask and which one's in the touch. Okay. So if this is in the Erlenmeyer, is this a strong acid, weak base, weak acid, strong base? Weak base. I gave it away in the title. It is a weak base. If it's a weak base, what would we expect the pH to be? 7, greater than 7, less than 7. Okay, so let's go ahead and figure out the pH of the solution before the titration begins. Step 1, as always, right, balanced equation. All right, so I know one component is this. What is the other reactant if it's just the ammonia floating around in solution? Right, it's just water. So then what would be one of my products? Yep, hydroxide, yep. Okay. Because that's the only thing in solution. I just have NH3 floating around, just pretending it's not a titration question. If I just said I have ammonia in solution, this is what you'd write. So don't get yourself confused by thinking, oh, that's titration. You've done it. Don't panic. They'll be okay. All right, so then the next thing, oh, I forgot to write this. You'll need this piece of information. So I know the concentration of this. What do I need to do in order to figure out the overall pH? What's my next thing I should be writing? It has letters in it. Yes, we need to write an ice chart. All right, do I have any of my products yet when I initially look at my solution? All right, there's nothing in there that. How come I can do this one in molarity? Right, it's just one volume. It's one component with one volume. I can use molarity, no problem. All right, so then we do minus x and some plus, 0.10 minus x plus x plus x. All right, what is an assumption I can make at this point to make our math easier? Yep. All right, since it's a weak base, I can assume that minus x is pretty small. That leaves me solving over here. Double check, make sure I got my x right. 1.8, 5. All right, how do I use that piece of information to find pH? Okay, if I do that, that tells me the what? pOH. Right, because X is telling me this, which is that. Is that pH reasonable for what we know about the solution? It is, right? It's basic, but not super basic, right? 'Cause it's a weak base, so it shouldn't be up in the 13s, 14s, but it has to be more than 7. So somewhere in that range. Good there? That should have been kind of a review question. Warm-up review. All right, I'm going to save B. We'll do that after break. I want to talk about what is the pH at the midpoint. So what is the pH equal to at the midpoint? Based on like one slide ago. All right, pH is at the half equivalent point, which is the midpoint. Half equivalent point, midpoint. pH is equal to pKa at the midpoint, or the half equivalence points. So at this point, I know pH is equal to pKa. Have I given you the pKa? Have I given you something that can help you find the pKa? Right, I gave you Kb. So how do I get from Kb to Ka? Okay. Yeah. All right, Kw is Ka times Kb. So, 14, 8, 5. All right, then what I need to do to my Ka to get to a pKa? What does the little p mean? Yep. All right, little p means take negative log of the thing I'm touching. Does that pH still make sense? Right, because if I'm at the half equivalence point, I'm not at the equivalence point, so I'm not equal moles. So I should still be fairly basic, but less basic than where I was, because I'm somewhere in the middle of the titration. Okay, when we come back after break, bring lots of paper, because these equivalence point questions, it took me 3 sheets of lined paper, and I write fairly small. So if you write bigger than that, you might need more paper to solve those problems. Something to look forward to. Yay! All right. So you will need a calculator for the quiz. So make sure you have one.